Hi, my name is George Woodrow, and I'm giving a talk on hermeneutics and Wolfram language. This is the fourth talk I've given at the Wolfram Conference. In each of the others, I've emphasized that my success as a designer / programmer has been greatly aided by my experiences in the arts and humanities. This talk is definitely a work in progress. It is part of a larger project to make a rigorous connection between metaphor as used in the arts and humanities and model as it's used in mathematics. It is my belief that education has become too siloed, too specialized. C.P. Snow's concept of two worlds, if anything, understates the problem. In the not too distant past, philosophy, science, and maths were not separated. Now it seems as though the humanities and sciences are armed camps. I think that the sciences need philosophy today more than ever. The talk is structured around the four-step process found on the computer-based maths website, and this is somewhat arbitrary, but it provides a familiar handle for the problem. Whoops. There we go. Hermeneutics is the theory of interpretation. It is a theory that everything is a matter of interpretation. Caputo goes on to say that there are facts, of course, but there's no such thing as a raw fact. Is this concept even reasonable? Recent discoveries in neuroscience can shed some light on the matter. It is pretty clear that what we perceive as naive reality is, in fact, a construct built from the mind using signals sent by the eyes, ears, and other sense organs. For example, we have no sensation at all of the rapid eye movements, as rapid movements the eye makes as it scans a scene, only the resulting construct. Visual illusions show how the mind can be tricked when reality is not what is expected. Further studies have shown that there's very little difference between normal perception and hallucination. In the case of normal perception, the brain verifies its construct with the outside world, and in the case of hallucination, it does not. Of course, this mechanism has evolved over millions of years for its survival value, so most of the time the construct has a close correspondence with the real world. Some parts of our perception mechanism are influenced by culture. We see artifacts of cultural transition, such as the rise of geometric perspective, invented by artists before mathematicians, and the change in art during the Renaissance. What we have, in fact, is a need to re-examine some of our basic assumptions about how we experience the world. Our mind is not a blank slate at birth. Our eyes are not cameras that provide a faithful recording of whatever we are looking at. In our everyday interactions, we are a living interpretation. What hermeneutics and its techniques, such as deconstruction, is aimed at is a way to examine the tendency to misidentify our constructions for reality. This tendency goes by many different names: prejudice, dogma, tradition. Science, and more specifically, scientists, are not immune. My main thesis is that whenever we build a model, we are making an interpretation. At some point, we will use metaphors to get a handle on any problem, and we need to recognize this if we were to make effective use of our wonderful tools such as Wolfram Language, our talent, and our time. I like this quote from Eugenia Chang. She may be speaking about pure mathematics in her quote, but I think that the issue is even more important for applications. It is certainly the case that in all major projects I have participated in throughout my career, it made a difference. For my process control project, the company's management and I thought that the main problem was to translate the protocols and procedures that the lab had established for results review into algorithms that could be implemented in code. It was only after we had finished the project that we discovered that the real problem was to find a way to analyze the state of the process in real time and to effectively communicate that knowledge to the technologists. The first approach led to the process of quality by inspection, while the latter led to quality by design. Sabine Hossenfelder quotes Paul Krugman. The The economics profession went astray because economists as a group mistook beauty, clad in impressive-looking mathematics, for truth. It is clear that sociology, psychology, and to a lesser extent medicine have the same problem. There are so many examples of poor papers published by someone armed with a statistics program and no deep knowledge of math that there is a term for it, p-hunting. Whether the problem is that the wrong kind of math is being applied to the problem or that the question is not well defined enough to even build a model, this is a question that needs to be resolved at this stage, or the entire project will be compromised. Of course, you might be able to find the appropriate tools, mathematical or otherwise, to approach a problem. If you're really lucky, you will be able to invent an entirely new branch of math to tackle the problem, as Newton did with the problem of gravitation. Okay. It is in this stage, translating to math, that knowledge of hermeneutics will have the most applicability to the success of a project. It is here that we prepare models of the problem that can be solved using math. In many cases, we can use models that already exist. In my case, I had to make my own algorithms. Fortunately, by that time, version 1 of Mathematica had been released, and I used it to solve my problems. I suspect for a lot of applications, building your own algorithms is the rule rather than the exception. When you look at it the right way, a model is conceptually very similar to a metaphor. It was this connection that started me on this path. A rigorous treatment of the connections between model and metaphor is still some years away. However, for now, it is sufficient to recognize that both of them are means for making connections between two things by analogy. It is this similarity that I use to justify the insights afforded by hermeneutics for mathematical model building. I will illustrate this with an example I used in building my process control system, having to do with Sitz and Leben. Sitz and Leben roughly translates to setting in life and refers to the context for a text, when it was written, where, in what culture, etc. In criticism, the text is the data. So this term asks the question, where did the data come from? For my project, I was dealing primarily with numerical data from a large clinical analyzer. So my questions were, where did the data come from, other than the obvious? What was going on the instrument at the time? What were the connections, if any, with other data? Can the data be trusted? If so, are there limits to the types of inferences that can be made from that data? First, I had to invent algorithms to estimate the bias and imprecision of the instrument in real time, the real Sitz and Leben of the data. Previously, this information was not computed. Second, the accuracy of bias depended on the accuracy of values for control targets, information that was not in the data set, but which needed external procedures for validation. When these procedures were not followed, the evaluation made by process control systems were incorrect. Third, it was critical to analyze the results for assays that were physiologically connected, a Sitz and Leben that is essentially orthogonal to the information provided by controls. The results of this analysis provided information that was not otherwise available, and because it depended on a stable human physiology, it produced more trustworthy information than other types of analysis. Previous efforts at quality control in the clinical lab failed because the designers of that system made incorrect assumptions about the process. They assumed that as long as maintenance was done, and there was a long checklist to ensure that it was, the imprecision of an assay was constant. They assumed that patient results did not need to be analyzed in real time. And it was assumed that the results were distributed normally. Most critically, they assumed that the process was nominally okay, and the QC system was designed solely to find failure. One of the most critical parts in the design of a model is to be fully aware of all the assumptions you are making. We've already seen one of the most critical and most overlooked assumptions in the previous section. Are mathematical methods we propose to use to solve problems appropriate for the question, or have we defined the problem well enough to design algorithms at all? In many cases, the most critical bias in any mathematical endeavor is the quantification bias. In Tricia Wang's TEDx Cambridge talk, The Human Insights Missing from Big Data, she says, we have this thing I call quantification bias, which is the unconscious belief of valuing the measurable over the immeasurable. But the problem is that quantifying is addictive. And when we forget this, when we don't have something to kind of keep that in check, it is very easy to just throw out data because it can't be expressed in a numerical value. It is very easy to just slip into silver bullet thinking as if some simple solution existed. The second notebook that I have has a whole list of references for all of these talks, and they're pretty much, this particular one is available on YouTube or TED. The good news is that it's now possible to do mathematics with objects that are not numbers, such as pictures, networks, and text. It doesn't matter that these are stored internally as numbers, just as it doesn't really matter how these things are stored internally in our brain. The mass and Wolfram Language can treat these complex things as entities. I believe that this approach will help with the soft sciences, the arts, and the humanities. It may even help with physics. The problem with application of mass to these areas in the recent past has been the drive to quantify everything, which leads to a loss of feel for the data, which in turn leads to questionable practices. For most problems, the trick is to take a bunch of data, feed it into the mathematical meat grinder, and get something edible out. If you don't know the Sitz and Leben of the data going in, you can't trust what's coming out. For hermeneutics, this is critical, but it is also critical for any problem taken from a mathematical viewpoint. Cathy O'Neill's book, Weapons of Math Destruction, and James Micken's address cover a lot of the problem, and I referred you to them. They're quite interesting. There is a reason that all the books that I read on modeling in the 1980s primarily treated only differential equations as the basis for a model. They were practically the only tools in the toolbox. Similarly, most of the statistical tools that were available practically forced the assumption that data was normally or log normally distributed. Today, of course, we have many new tools, and our statistical palette is very large. Techniques such as neural nets and the genetic algorithms hold the promise that more realistic models can be made. Even though these techniques are being used and misused, they are in their infancy. After all, differential equations has had a 300-year head start. One glaring issue with machine learning is that they are treated as black boxes. Changing what appears to be minor parameters can radically affect the outcome. This phenomenon needs to be understood before using math for mission-critical tasks. As we understand neural networks better, I am sure that we will be able to drop some of the assumptions that we are forced to make, resulting in a more useful result. Other things may need to be improved as well. For example, if we want to do more than bag of words analysis of text, we will probably need the equivalent of the Oxford English Dictionary instead of the present relatively simple dictionary. To summarize, at the foundation of any model building is a need to understand all the assumptions that you are making, even if you need to keep the assumptions, knowing that what they are sets limits on what you can do. Hermeneutics has been in the business of examining assumptions for a very long time, and it is a useful tool. In addition, knowing what the assumptions are, you might be able to invent new math to eliminate the need for some, if not all, of the assumptions. Wolfram Language is a great tool for inventing new maths. Before the middle of the 19th century, it was generally believed that if you prove something about mathematics, you were proving something about the real world. The invention of non-Euclidean geometry was the end of this view, although it may be widely believed by non-mathematicians. This discovery was the main drive behind the search for rigor that characterized 19th and 20th century mathematics. It is pretty clear that Euclid chose his algorithm so that he could prove theorems that corresponded to facts about real straight lines, circles, angles, and so forth. The same applies to the axioms for fields, algebras, and other parts of classical mathematics. It was only when axioms were devised that were consistent, but which did not yield consequences directly applicable to reality, that the profound separation between math and physics, for example, was realized. This is a good thing, because we are now free to invent new mathematics that is interesting to us. If there is an application, so much the better, of course. The point of computation is that the computation itself does not add anything that was not logically implicit in the initial hypothesis. Factoring a polynomial, for example, does not yield anything that was not already there, although having the factors means that you know the roots of an equation. Wolfram Language is essentially a set of rewrite rules. So the construction of the language brings this point home. Computation, therefore, does not add any pixie dust that magically removes any biases or assumptions that were present in the original model or the data. The expression garbage in, garbage out should be on the minds of anyone using math to solve problems. Okay, you've got your number, 42. What are you going to do with it? As Arthur Dent found out, if you don't really know what the question is, it is difficult to know what the answer means. Unless we are very careful, we, or especially the people we are doing the math for, will misinterpret the results. If the original model uses any data, we not only need to know what the uncertainties of the data is, but we need to know what the computation does with this uncertainty. Many types of computation can give an answer, but the uncertainty is so large that the utility of the answer is essentially zero. Another problem is that good results may be taken to mean that a model may be used to say something about the world beyond the context of the computation. The poster boy for this issue is the Ptolemaic model of the solar system. Given that the problem was to predict the positions of the planets with an accuracy equal to that of the measurement error of the time, the Ptolemaic model was a good model. It gave better results than early interpretations of the Copernican hypothesis. Of course, there were several problems with the old model. When better data were available, better models showed the error of the old model's computations. The main problem, of course, was that the model was accepted as dogma for a context for which it was not appropriate. Over time, models such as Clerk-Maxwell's mechanistic interpretation of electrodynamics or the planet Vulcans did not outlive their usefulness, but not all of these ideas do. As Katie Mack has pointed out, it may turn out that quantum mechanics might just be tons of epicycles on top of each other to get everything to work out. Okay, what's all this got to do with Wolfram Language? Wolfram Language makes it much easier to use mathematics to solve problems than any tool in history before it. I don't know of anyone in my generation who was involved in science who did not wish that he or she had Mathematica in school. Wolfram Language is a game changer in at least two broad areas. First, Wolfram Language is easy enough to use that people who are not mathematicians, physicists, or engineers might be enticed to use it. I grant that this is not going to be easy given the way that most K-12 education has hidden the beauty of math from 90% of the population by redefining what math is to something that is really boring and then making it difficult to escape the trap that the students are placed in. However, I am optimistic that it will be possible to interest philosophers and others in the humanities camp to use Wolfram language. Math has been in both of C.P. Snow's two worlds for most of its existence, and I am certain that many paths exist to make this a reality again. And Stephen Wolfram mentioned this in his keynote last night when he said that, mathematics really is a liberal art. I believe, and a lot of other people believe, that we need philosophers to help build this brave new world. Simple computational thinking or mathematical thinking is only a first step. Secondly, Wolfram language is the ideal tool to deal with the issues inherent in the current misuse of maths, particularly machine learning. As more people use machine learning, more people, those who have subject matter expertise, not mathematical knowledge, will come to see the inherent weakness in using a tool whose inner workings are a black box. People will figure out how to penetrate this black box, at least well enough to understand the way uncertainty is handled in any model that uses machine learning. And I think some of the talks in this conference illustrate this. The primary danger here is that we are so enamored of our beautiful tools that we fall victim to what Mickens calls technological manifest destiny. Those of us at this conference may not even realize its presence, much the same way that fish are not aware of water. The key point is that technology is not neutral. History is littered with the consequences of forgetting this. We can see the results all over. Entire fields of thought are being devalued because they are being seen as inconsequential to the STEM fields. Other fields are being replaced by changelings that follow the forms of physics, but without understanding. Richard Feynman called it cargo cult science. Large numbers of people are rejecting science entirely rather than being reduced to a number because there is no connection to their actual subjective lives. Steve Jobs was right. What we need is the marriage of science and the liberal arts. Okay, and there's the further reading, and so my rant is done. Okay. And I really hope that you look at some of this further reading. The Caputo book in general was what got me off on this jag. I found it in the bookstore in London, and it's really quite interesting. And if any of you wander over into that section of the bookstore, you might find some other things. Okay, any questions, comments?